opportunity, and thank you everybody for coming. This is a work in collaboration with Enrique Ramirez. I will talk about a relation between polyhedra and relation modules. These relation modules were introduced by Futorni, Ramirez, and Zhang in 2019 as a attempt to generalize Gelfand setting construction for simple finite dimensional modules for GLN. First off, we need to define the set of relations. And a subset of relations is a subset of this big set. Actually, this is a graph over when the set of vertices is that, a triangular configuration. R plus is the all going down a road between consecutive rows. R minus is the dual graph, or a road going up a road between consecutive rows, and the special graph or possible horizontal road in the top of the triangular configuration. In a subset of, in a subset of this onion is called the zero relation, and we denote by GC the graph associated with this set of relations. For example, we have CK plus. This, in particular, this one is the set of relations for generic Verma modules, the dual CK minus, the onion of that set of relations. This one is the standard set of relations for standard Gelfand setting modules. And this one is associated to cospiral modules for GLN. We will work in the category GLN modules. So, the classical definition of Gelfand set tableau is a triangular arrangement with interest in the complex number. For subset of this vector space, we will denote by TA the set of all Gelfand set tableau over the set. Technical definitions. Given a set of relation T and Gelfand set tableau, we say that this Gelfand set tableau satisfies the set of relation with satisfy this condition for any arrow in the graph associated to set of relations. Moreover, it satisfies these conditions if only if both vertices are the same connected component. We say that the Gelfand set tableau is a serialization. For example, we have the set of relations and two Gelfand set tableau. Both Gelfand set tableau satisfy the set of relations. This one is a derealization, but this one is not a serialization. We have three component, connect component, and 1 minus 0 is an integer. Okay, we will denote by this set, the set of Gelfand set tableau with the top being 0. Now, we fix a Gelfand set tableau satisfying a set of relations. We denote by BCTL the set of all Gelfand set tableau. Integer translation of Gelfand set tableau satisfying the set of relations. Over that, we denote by VCTL the vector space with that basis. Now, we say that the set of relations is called admissible if for any serialization the vector space previously defined has the structure of GLN module over the Gelfand setting formulas. Okay, this is the weight relative to Cartan's voucher of GLN. If the set of relation is admissible, we will call the vector space is a relation module. Okay, it is important to note that Futorni, Ramirez, and Zhang in 2019 classified all admissible set of relations. As a consequence, we have the first example in this lecture. CK, CK plus, and CK minus are admissible set of relations. In the case where the set of relation is C1, they get rewrite the Gelfand setting theorem, this Gelfand setting theorem. Okay. To say about polyhedra, we need to establish what is the closed half space. For us, our closed half space are this for any row ij in the graph associated to set of relations. Any point in the intersection of all closed half spaces is called C pattern. We will denote by WK, the kth wave linear map. Okay, with that, we can define the polyhedron. PC, PC lambda mu, with fixing lambda and mu a vector in this vector space. PC is the polyhedron of the set of all C pattern. PC lambda is the set of all C pattern fixing the top of the Gelfand setting tableau by lambda. And PC lambda mu is the C pattern fixing the top by lambda. And the vector weight by mu. It is easy to check that PC is always unbounded. It is enough to consider any self-relations. For example, and put the thing in try. The set of this C pattern is unbounded inside the PC, the polyhedron PC. Now, for PC lambda, it's a polytope, it's a bounded, if only if the minimal, the maximal minima point in the graph associated to set of relation belong to the top of the triangular configuration, the set of relations. Okay. We are interested of the how to say the integer translation for a Gelfand setting tableau. This point is called L integral point. This is the as a first theorem we can we give a relation between the number of L integral points inside of the polyhedron with the dimension of the relation modulus and the multiplicity of the weight space. If we consider a relation modulus, we denote by lambda the top of the Gelfand setting tableau, and by mu the vector of weight. So the polyhedra PC lambda and PC and PC lambda, the number of L integral points inside in this polyhedra is equal to the dimension of the relation modulus. And for PC lambda, the number of the L integral points inside of this polyhedron is equal to the weight space V mu. When consider the particular case of the set of relations C1, we obtain as a corollary the results of Gelfand-Selivinsky of 1985, I think. Because this relation model is isomorphic to the simple finite dimensional model for GLM. Okay. But we can apply this theorem for more relation set of relations. For example, for generic Verma modules, we consider C1 plus and co-spiral modules. In this case, we consider the set of relations C2. We only apply our theorem. Okay, we are interested to study the dimension of the minimal phase contained certain point of the polyhedra. For us, for this lecture, the minimal phase contains certain points fixed is in sense of the minimal dimension possible of the phase contained that point. For compute this dimension, we need to define a tiling of the, we need to define a partition of the set of relations. Sorry, set of vertices. Okay, in this sense, we say that two vertices are the same equivalence class is only if there exists a walk. Is not necessary orientations. But when see the C pattern, all interests associated with this walk are equal. We have this one is called a tire. The set of the partitions induced by this relation is called tiling of the C pattern. We are interested in two special tails, top free and top bottom free. A tailor is top free with if doesn't intersection with the top of the triangular configuration, the top of the set of vertices, and bottom top free if the tail does an intersection between the top of set of vertices and the bottom set of vertices. Okay, for example, we have three set of relations with respective C pattern and with respective tiling. For example, we have two interests equal, but there is not a walk connecting these vertices. Okay. To compute the dimension of the minimal phase containing C pattern, we define a matrix, a tiling matrix. The tiling matrix is a matrix with integers, positive integers in tries, and this in tries is counting the number of intersections between the tiling, the top free tile, with the ith row. For example, this is the tiling matrices with respect to the before previous example. Yeah. Of course, the tiling matrices, the tiling matrices depend on the chosen order of the top three, but we are interested to compute the dimension of the kernel. And from now on, we will enumerate the top three tails from left to right and to bottom to top. Okay. Fixing a set of relations and C pattern, we denote by lambda the top of the Gelfand set tableau, and by mu the vector of weights. We say this is a first step to classify the dimension of the minimal phase containing the C pattern. In PC lambda, remember, recall that this is the polyhedron of all C pattern fixed in the top by lambda. We consider the tiling, the partition. If the all tails intercept the top, in this case, this C pattern is a vertex in this polyhedron. For it. Now, in the PC lambda mu, we will if the tiling does not have top, the bottom free tile, that means all tile intercept the top and the bottom, this C pattern is a vertex in this polyhedron. Now, to compute the dimension, the minimal phase of the polyhedron containing the C pattern, we need just to count the number of the tails to determine the dimension of the minimal phase in this polyhedron. So we consider the partition, the number of the tails is equal to the dimension of the minimal phase of the polyhedron in PC. Yeah? Now, the dimension of the minimal phase in PC lambda, fixed in lambda, the top lambda, containing the C pattern is equal. We need just to count the number of the top three in the tiling. Now, for the polyhedron PC lambda, we just need to compute the kernel, the dimension of the kernel of the tiling matrix. For example, the previous examples. In this case, we have 1, 2, 3, 4, 5, 6, 7. Here, the dimension of the minimal phase contained this C pattern is equal to 7. Now, it's very interesting in this case, this point is an edge. Okay, this is a reference, our motivations, and thank you for your attention.
Questions, comments? Not just think we start our next talk